I say a function fx is differentiable at a point x equals a of its domain when limit x tends to a fx minus f of a upon x minus a exists finitely, right? And then we said this limit existing means this limit existing from the left of a and this limit existing from the right of a, and both of them are equal to the same number, which is this, right? And therefore, alternatively we define left hand derivative of f at a. What was that? Limit x tends to a from the negative f of a minus h minus f of a whole upon a minus h minus a, and then we replace x tends to a from the negative from h by h tends to 0. Eventually getting limit h tends to 0 f of a minus h minus f of a whole upon a minus h minus a gives you minus h. And similarly we defined right hand derivative of f at the domain point x equals a as what? Limit h tends to 0 f of a plus h minus f of a whole upon a plus h minus a, which is just h. Fine. So having defined the left hand derivative of a, left hand derivative of f at a and right hand derivative of f at a, we said LHD of f at a should be equal to RHD of f at a is what is the meaning of this limit existing finitely. Fine. Now what we discussed in the last lecture was that whenever a function will be differentiable at a point, it will necessarily, compulsorily be continuous at that point. I also explained you a geometric, natural, intuitive way to understand this particular concept. Moreover, we formalized it by proving it in complete manner. So what did we learn? We learned that differentiability at a point implies continuity at that point. Fine. Once we had understood this by formalizing a proof of this, in fact understanding it in geometric sense, because when you say differentiability at a point, you need chords to be existing on the left hand side of that point or on the right hand side of that point on the curve. For chords to exist on the left hand side and right hand side of the point at which tangent you wish to show is existing, curve should exist on both sides of that point, which implies continuity at that point. That means there is no break. The curve is not broken at the point at which you are testing your differentiability, or at which the function is already differentiable, which therefore implies that the function is continuous at that point. Okay. And I told you, if differentiability implies continuity, is it true that continuity implies differentiability? Answer was a big no. Continuity does not imply differentiability. A function may be continuous at a point but may fail to be differentiable at the same point. Well, you might ask me, what is that function, where is that function which possesses the feature of continuity at a certain point of its domain, but when I check the differentiability of the same function at the same point at which it is continuous, it's not differentiable. That means corresponding to that point, the curve is unbroken, there is no break, there is no hole, there is no gap. A continuous form is there in the curve corresponding to the point, suppose A of the domain. But when I go and see corresponding to the point A at the point A comma f of A in the graph of the function f, I cannot draw a unique tangent. Yes, either there are infinitely many tangents to be drawn, right? That means somehow there is a corner point in the graph corresponding to the point A. Okay, that is why the function is continuous at that point but not differentiable. Well, the example of such a function is fx equals mod x for all x belonging to R. This function is continuous. This function is continuous at x equals 0 point of its domain but not differentiable at the same point. Fine. If I make you recall about the graph of the modulus function, the graph of the modulus function was like this. This is the graph of fx equals mod x, where this is your x-axis and this is your y-axis. Fine. And this is your 0, 0. Okay? If this is fx equals mod x graph, you can see there is one corner point in the graph. The corner point is this. Corresponding to the point 0 in the domain, 0, f of 0, which is 0, 0 is a corner point in the graph of, in the curve of y equals mod x. Definitely at this point infinitely many tangents can be drawn to the curve y equals mod x. That means function is not differentiable at 0. But if I talk about the hole or a gap or a break in the graph of the function, there is no break. I can take my pencil, in one go I can complete the drawing of this graph. I will not have to pick up my pencil in way between in order to complete the drawing of the graph. Because there is no hole, no gap, no break, it's an undisturbed graph, completely continuously drawn. That means it is continuous, but because there is a corner point, that's why it's not differentiable at the point 0. So that's why it's written the function is continuous at 0 but not differentiable at 0, because corresponding to 0, 0, 0 point in the curve, over there the function is continuous. There is no break, no hole, no gap. But if I talk about 0, 0 point on the curve, it is a corner point and therefore there can be infinitely many tangents which can be drawn, because of which it's not differentiable at 0. Fine. Already while studying continuity, we have proven that modulus function is always continuous. So, we know modulus function is an everywhere continuous function. Okay, modulus function is an everywhere continuous function. That means it is continuous on the entire real line, which implies fx equals mod x is continuous on the entire real line, which implies fx equals mod x is continuous at x equals 0. If it is continuous for all real numbers, it is definitely continuous for 0. Fine. I have to show this function was continuous at 0 but it is not differentiable at 0. So intuitively again by just the graphical approach we have understood that because 0, 0 is a corner point, function is not differentiable at the domain point 0. But formalized approach will be what? Any function is differentiable at a point provided left hand derivative of f at that point is equal to the right hand derivative of f at that point is equal to a finite value, right? That is what is the condition. We learned it in the definition of derivative. And therefore over here I will be now calculating the left hand derivative of mod x at 0, then right hand derivative of mod x at 0, and we will see that they both do not come out to be equal, and then I will tell you the reason also. So let's begin with left hand derivative. Left hand derivative of fx at x equals 0 will be what? Limit h tends to 0, f of 0 minus h minus f of 0 whole upon minus h. Right? Just see. H tends to 0, f of a minus h minus f of a whole upon minus h. Here my a is 0, so limit h tends to 0, f of 0 minus h minus f of 0 whole upon minus h. Right? If fx is equals to mod x, f of minus h, this is minus h only, I can write it as limit h tends to 0, f of minus h minus f of 0 upon minus h. F of x is mod x, so f of minus h is what? Limit h tends to 0, f of minus h is mod of minus h minus f of 0 is mod of 0 upon minus h. The first question says that the function is defined from collection of all reals minus singleton 0 to the collection of all reals like this. This function can be made continuous at x equals 0 by defining f of 0 as what? So basically if you talk about f of x is given to you as 1 upon x minus 2 upon e to the power 2x minus 1. You can make this function continuous at 0 by defining f of 0 as what? F of 0 should be defined as limit x tends to 0 f of x. If this happens to be true, in that case I can say that the function f is continuous at x equals 0. But for this we need to first compute limit x tends to 0 f of x. What would this be? Limit x tends to 0 f of x is actually limit x tends to 0, this function. What is this? E to the power 2x minus 1 minus 2x whole upon x into e to the power 2x minus 1. Now you can just use the very expansion of this exponential function. What is it? E to the, or I should write 1 plus 2x square by 2 factorial plus 2x cube by 3 factorial and so on minus 1 minus 2x as it is. I am just using the expansion of the exponential function, and then in the denominator as well this is 1 plus 2x square by 2 factorial plus and so on minus 1. 1 minus 1 gets cancelled, 1, 2x, minus 1, minus 2x, everything gets cancelled out. What you are left with is limit x tends to 0, this becomes what? 2x square by 2 factorial, then 2x cube by 3 factorial. So basically 2x square can be brought out common. You are left with 1 by 2 factorial and then rest of the terms have x term in them. How? This will be 2x cube by 3 factorial. So 2x square has been brought out. 2x is left by 3 factorial and then so on. Fine? Whole upon, if you see carefully, this is 2x square, right? This is 2x into x, 2x square plus 2x whole square into x by 2 factorial and so on. So what I do in the denominator is I take out 2x square common. I am left with 1 plus. So from here 2x square has been brought out common. So you are left with 2x by 2 factorial and so on. Clear? You are left with 2x square has been brought out common. So 1, 2 is left, 1x is left and therefore 2x by 2 factorial is left. Rest all the terms are going to have at least one x term. Here also at least one x term will be there in all the next terms. So you can see 2x square gets cancelled. You are left with 2, 1 by 2 plus 2x by 3 factorial plus and so on whole upon 2x square is cancelled. You are left with 1 plus 2x by 2 factorial and so on. Now see, as limit x approaches 0, this complete thing becomes 0 plus 1, that is 1. So denominator is 1. This complete thing becomes 0, so you are left with 1 by 2 plus 0. So eventually what you get is 2 into 1 by 2 whole upon 1, which is 1, and therefore the limit that you get for fx as x approaches 0 is 1. F of 0 should be equal to 1 for f to be continuous at x equals 0, and therefore option number B is the correct one. Moving on to the next question, we have if f is a function defined from collection of all reals to the collection of all reals like this, then compute the value of this limit. So what is the value of this limit? Let's see. It is limit x approaches to 2, fx minus f of 2 upon x minus 2. So my fx is this. If you simplify, see here x is approaching to 2, so I cannot take these values. F of 2 I need directly, I am going to plug in 1 over here. I am wanting limit x tends to 2 f of x. Now if you simplify this, what you get? You have x square minus 3x plus 2. Right? And in the numerator you have x minus 2. Okay, so this becomes what? This is x square minus 2x minus x plus 2. Right? So this becomes x minus 2 whole upon x, x minus 2 minus 1, x minus 2. So eventually you get x minus 2 upon x minus 2 into x minus 1. This is 1 upon x minus 1. Okay? So basically your f of x is 1 upon x minus 1. Now plug in place of over here. So this is 1 upon x minus 1 minus f of 2. F of 2 is 1 whole upon x minus 2. 1 upon x minus 1 minus 1 whole upon x minus 2. So what you get is 1 minus x minus 1. Or I should write 1 minus x minus minus plus 1 whole upon x minus 1 into x minus 2. So this becomes what? This is 1 minus x plus 1. So this becomes 2 minus x whole upon x minus 1 into x minus 2. I can write this as minus of x minus 2. Right? And so I am left with minus 1 upon x minus 1. It is actually limit x approaches to 2. So as x approaches to 2, I get just minus 1 as my answer, and that is the required limit. Clear? Easy enough question. Next question is fx is sin x by x when x is non-zero. What do you think is going to make this function continuous at x equals 0? This function will be continuous at x equals 0 if f of 0 is defined to be equal to limit x tends to 0 f of x. So what is limit x tends to 0 f of x? This is pretty simple. Limit x tends to 0 sin x by x. You know that as x approaches to 0, when x is very, very close to 0, sin x, graph of sin x is almost same as that of the identity function. So sin x approximately becomes equal to x. So x upon x gives you 1, and this is how, this is the limit that is equal to 1. So limit x tends to 0, f of x is 1. You should actually define f of 0 to be 1 if you want that your function should become continuous at x equals 0. So for fx to be continuous at x equals 0, f of 0 should be defined as 1. Clear? Next question says if f of 2 is 4, f dash 2 is 1, what is the limit of this expression? Let's calculate. What is the limit of this expression? This is limit x approaches to x into f of 2 minus 2 f of 2 plus 2 f of 2 minus 2 fx whole upon x minus 2. Clear? Now this becomes what? This is limit x approaches 2. You can take out f of 2 common from here. You're left with x minus 2 whole upon x minus 2 minus, let me write, plus limit x approaches to 2 minus 2 f of x minus f of 2 upon x minus 2. I'm just simplifying the expression, nothing else. So this gives me just f of 2. This is minus 2. Limit x tends to 2, fx minus f of 2 upon x minus 2, which is what? F dash 2. F of 2 is given to me as 4. F dash 2 is given to me as 1. 4 minus 2 gives me 2. And therefore, the answer of this expression is basically nothing but 2. Easy enough, just need to manipulate it accordingly so that you can use the very derivability definition as well. First question is giving you the value of f, x is not equal to a, the value which should be assigned to f at x equals a so that it is continuous everywhere. Okay, so for it to be continuous, what do we need? F of a should be equal to limit x tends to a f of x, and f of x is what? 2 minus x upon a whole to the power tan of pi x by 2a. Right. Now over here you can see there is power. I want to get rid of this power. I will be applying log both sides. I am going to get log of f of a equals, now log is a continuous function, so log of the limit is limit of the log, limit x tends to a. This is tan of pi x by 2a into log of 2 minus x by a. Right, so the power is going to come ahead of log. This is the power log of this. Fine. Now you can see over here, if I just get rid of this tan and I instead write it as tan is nothing but 1 upon cot. So I can write tan as 1 upon cot of pi x by 2a. Now over here you can very easily see that this is of the form 0 by 0. So I will be applying the L'Hopital rule. When I differentiate the numerator and the denominator, what is it that I get? I get 1 upon 2 minus x upon a, 1 upon 2 minus x upon a into d by dx of 2 minus x upon a, which is minus 1 upon a. So this is minus 1 upon a whole upon, what is this? This is minus cosec square pi x upon 2a into d by dx of pi x upon 2a, which is pi by 2a. And over here you basically have the limit. Fine. Now if I move ahead, I can further write this as minus 1 upon a into 2 minus x upon a. This thing divided by this expression means multiplied by 1 upon cosec square pi x by 2a, and this is 2a by pi. So from here you can see a cancels out, minus minus cancels out, you're left with 2 by pi, and here you have sine square pi x by 2a, sine square pi x by 2a whole upon 2 minus x by a. When you apply limit x tends to a in here, you basically get limit x tends to a, this becomes what? This is a, so pi a upon 2a, that is pi by 2, which is 1. So you get 2 by pi into 1 upon, again x tends to a, so you get 2 minus 1, again 1. So this is 2 by pi. Fine. If you are getting log of f of a is 2 by pi, what is f of a? It is e to the power 2 by pi, right? Because if you take exponential, you basically get e to the power 2 by pi, and here you are left with f of a. Fine. So f of a turns out to be e to the power 2 by pi. Let's look at the next question. In the next question, what is it that we are going to have? Let's see. Okay. So the next question says ax cube plus x square minus a plus 2x plus a whole upon x minus 2. Let's talk about this question now. It is saying this is continuous at x equals 2 then. Now the moment I am saying this is continuous at x equals 2, that means limit x tends to 2, f of x is equal to f of 2. Limit x tends to 2, f of x to be equal to f of 2, That means this limit is existing, right? For this limit to exist, limit x tends to 2, this particular expression's limit is existing as x approaches 2. For this to exist, definitely x minus 2 should be a factor of the numerator, right? X minus 2 is a factor of ax cube plus x square minus a plus 2x plus a. Factor of this means 2 is a 0 of this. That means in place of x, if I put 2, I am getting 0, right? So you get 8a plus 4 minus 2a minus 4 plus a is 0. Minus 4 plus 4 cancels. You are left with 8a minus 2a, that is 6a, 6a plus a, that is 7a is 0, or I can say a has to be 0 for this function to be continuous at x equals 2. Fine. Looking at the next question, we have fx is defined on 0 to pi by this particular branch function. Definition: if f is continuous on 0 to pi, then what is the value of a and b? Obviously, we are to check the function's behavior on these breaking points, which is pi by 4 and pi by 2. If I talk about f of pi by 4, f of pi by 4 is actually equal to pi by 4 plus a into root 2 into sine of pi by 4. Sine pi by 4 is 1 by root 2, root 2 cancels, you are left with pi by 4 plus a. Value of the function at pi by 4 is same as limit as x tends to pi by 4 of the function, right? So what is limit? X tends to pi by 4 f of x. Both of these will be equal. So as x is approaching to pi by 4, I am getting 2x cot pi by 4 plus b, that is 2 pi by 4 cot pi by 4 plus b. Cot pi by 4 is 1, so you are left with 2 pi by 4 plus b, which is pi by 2 plus b. Both of these are equal because the function is continuous at pi by 4, so you are getting pi by 4 plus a equals pi by 2 plus b, or a minus b is pi by 2 minus pi by 4, which is pi by 4. Similarly, if I talk about value of the function at the next point, that is pi by 2, if I take it over here, what is it that I am getting? Cot pi by 2 is 0, so I am just getting b. So f of pi by 2 is b. And if I talk about limit x tends to pi by 2 of f of x, it is actually this. So it is a cos 2 pi by 2, so it is a cos pi is minus 1, so this is minus a, and sin pi is what? This is pi by 2, so sin pi by 2 is 1, so this is minus b, so minus a minus b. Again, both of these are equal because the function is continuous at pi by 2, so you are getting b equals minus a minus b, or 2b is minus a. If 2b is minus a, so see we have two relations in a and b, so obviously I can compute a and b now. So if 2b is minus a, or I can say that b is minus a minus b, that means a is minus 2b, so minus 2b minus b is pi by 4. So minus 3b is pi by 4. b is minus pi by 12. If I am getting b is minus a minus b, I am getting b plus b, that is 2b is minus a, or a is minus 2b. Right? If a is minus 2b, I am getting minus 3b equals pi by 4, so b is minus pi by 12, and in that case a is what? Minus pi by 12 equals minus a, so a is pi by 6. So a turns out to be pi by 6 and b turns out to be minus pi by 12. Clear?